Right. Okay, I think we are on air now. Okay. Right. In the name of God, the compassionate, the merciful. Thank you everyone for joining us today for the is it the fourth? I think yes, it's the fourth session in the series of Introduction to Idris. Which is going to be like the penultimate, or maybe I will extend it for another session. I'm not sure. Now, today's session will be on the data types, algebraic data types. And given that you guys are Haskellers already, so I will just flash through it and try to make it as quickly as possible to where things get different from Haskell. So the book presents like 5 classes of data types. It gives them names. The first of them being enumerated types, and those the definition is this. That's the types defined by giving the possible values directly. And an example of that is here. The possible set of possible directions, the 4 possible ones, north, east, south, west. This is a data type with 4 values only provided directly. Now, this is in as you can guess, probably you can also present this data type this way, right? That's just the same. But if you are doing the multi-line, it's a good practice to put them underneath the operator upstairs. Now, there are also union types, which are only slightly different because now, you know, in addition to the kind of labels of each of the values, there are also additional data that they carry around. So, for example, if I'm about to have a data type for shapes, a triangle usually has a base and also what's that called?
Height.
The height, yes, the height. A rectangle is usually determined using its 2 perpendicular sides. A circle is identified by its radius. Now, so as you can see, in addition to the labels, there are also values attached. So this is what Idris calls union types. Now, by the way, in the book, there are examples about how to enjoy TDD with these. I'm just not going to get into them. Now, here is something slightly different. I think this might be a bit unfamiliar. Now, let me just maybe comment this one out. Right. Now, you can produce the same ADT using this alternative syntax, which is more verbose, but it's used because it can help with certain things that the previous notation couldn't, and we're going to see some of that. Now, let's read through this. What this is saying is that shape is a type. And it also says that, okay, there are 3 data types. Sorry, there are 3 functions which are constructors of this data type. And these are the signatures. Now, these being functions, as you can see, they all return shapes, right? That's one of the extra pieces of syntax that you need to put in, which you didn't have in the previous notation. Now, how many of you are familiar with generalized ADTs or GADTs, or some people call it GADTs? Right. Okay. So, right. Okay. So this notation was in Idris from day one, and that gives us the GADT or the GADT as well, because you know, it's technically there is no restriction on the return type of these to be shape, right? Now, even though these are constructors of that data type, there can be variations as you're going to see, right? So that's the more generalized and more verbose notation. Sometimes that is the only notation that you can use. There are recursive types, which are just like union types with the difference that they kind of refer back to themselves. So here is a data type for pictures. A picture can be either a primitive shape or a combination of two pictures, or a rotation of a picture with a certain degree, or a translation of a picture to another location. And so what is there to observe is that this picture thing, the name of the data structure of the data type is showing up both on the right-hand side and on the left-hand side, which is why we call them recursive. Now, so then the next class of data types that the book presents is what it calls generic types, and that's data type that's genericity by type, as we're going to see in the next session, where I'm going to give you a tour in genericity and polymorphism. But for now, all we need to know is that these data types are parameterized by types. Now, you have seen perhaps maybe, so if I show you the constructor, is this, by the way, is my screen readable enough?
Yeah, of course.
Yeah, Sander, you told me the previous time that you might have difficulties. Is this good for you?
No, it's fine. It was when we were in person. It was far away, but now it's fine.
You might want to make the font bigger for people watching online.
That was the question, actually.
But for people watching online on like a phone,
right? Okay.
It will be too small for that.
Right. Okay. Is it also? Let me see. What is?
Control scroll should work.
Yeah. Well, unfortunately, it didn't.
Control plus, I think it is actually.
Yes, you're right. I think this is good. Okay. I'm guessing that this is now better.
Yeah, right. Sure.
Okay.
I don't know. I'm not on a phone.
Right. So what is there to notice is that you see, maybe is something. It's a higher kind of type, which means that it takes a type and returns a type. Now, so as you can see, there is a type parameter here, and it has two constructors. There is maybe of a type. There's nothing which gives you a maybe of a type, or there is just, which takes a value of that type and gives you a maybe of that type. And so yeah, you here is the list of the type classes that, or as they call it, the relevant interfaces of data type. Now, so like I said, the observable thing here is that there is a type parameter that this maybe type takes. Now we are going to dive into an example of these kinds of data types. There is, let's say that we want to have a tree of, and that's going to be like, what was that called? This is the trees that don't have labels on the leaves. I don't recall the name of that class of trees, but anyway, it's that is the kind of tree that we are going to deal with, and that is the one that is suitable for the algorithm that we're going to show. So the idea is that no, I gave you the wrong description. This is not that. This is just labeled trees. Now, so the idea is that every node in this tree has a left branch and a right branch, and on every node there is an instance of a type that is the type parameter of this data type. And sometimes the subtrees to the left or to the right are empty. So that's why we have two type constructors here, empty and node. And specifically, I would like to draw your attention to this type parameter and the fact that it shows up here as a type level, and also used as a type level underneath. Now, here is a new piece of syntax. This is a directive of the compiler. It says that if you want to perform case split or cross generation for this data type tree, then these are the good names for you to go through. Right. So that's that. Now, without any further ado, we would like to have a function which helps us insert new elements into our binary search tree, and as you can see, this is a binary tree because there are only two subtrees, one to the left and one to the right, that we can have. Now, well, oh, no one's talking to us.
No, it's
no one's talking
James.
to us. Right. Okay. Fine. So right, the usual TDD. Jan, what do we do first?
We case split. Well, we generate the first case. Sorry.
Okay. In fact, there is
Add
also
clauses.
the possibility of doing some of the work, right? But that's fine. We can generate the definition, and then you see the two arguments, or the two parameters to this function. There is x, which is kind of the generic name, and there is tree. And this is called tree because up here, the first alternative that we gave to the compiler is tree with little characters. So that's why that directive is useful. Now, here is something for you, Mikhail. Let me. So you see, if I now double click here, there is no little bulb, right? But if I save it and then double click, then the bulb shows up, right? I think that's where you got stuck. Now let's go for the at clause again, right? Now, thank you, Jan. Niels, what next?
Base case.
On
You can like use the I don't know.
you want a little help?
Yeah.
You would want to do K-split, right?
Yeah.
Now the question is, what do you K-split on?
The tree.
That's right. So, okay. Now here are your two cases. Now, then let's see, Mikhail, what do you do then? Okay, it's too small. Let me.
No.
We have it on television, but he's still watching on the computer, so I don't know what he's doing.
Ah, okay. That was you paying attention. Okay. Okay.
We create a tree where y is x, or
Well, do you know
Sure.
do you know the logic of a binary search tree and the insertion into it? Do you know that? Maybe you don't. Maybe I should explain that. So a binary search tree, you're trying to maintain an order in your data structure by you know, putting the elements that are less than your own node to the right hand side, and the ones that are greater than your own node the label of your own node to the left hand side, right? Now this enables you to have a logarithmic search possibility. So if you're searching through the binary search tree, you're guaranteed that you will get to a response about where that element is, or in fact saying that no, it's not there. This is the specificity of a binary search tree. So it's an element, it's a sorted tree, you know, and the sorting is that the ones that are less than go to the right, the ones that are greater than go to the left, and always there is this distinction between what is the top, what is to the top, and the subtrees, and this same the same rule is recursively pushed down, right?
But in this case, we don't have specified that you can order them. Like on the parameter, like on the types.
Ah, that's a very good point. That's a very good point. So you would like to start by making sure that this type is ordered, right?
Mm.
Okay. Good. Then
check if x is greater or less than y, and recursively call insert on the next tree leaf.
we can also do that. We can also do that. Is there anything easier that you can do?
Use TDD.
Okay, we're about on.
On the base case.
On the
Like
base
insert.
case.
Yeah.
Okay. On the whole, I guess you mean.
Yeah, yeah. On the first hole, on the base case, yeah.
Now, let's see. So you can see out of the possible, you know, expressions that it can search through is an empty tree, or this one is the more interesting one. That is the one that we would want, right? Yeah. Okay. Now, James, let me first of all rename these so they make more sense.
Yeah, I was going to ask if is there a way to let the compiler know that if there are two trees, like in the node example, if you can name them left or right.
You can name them whatever you want.
No, but you like with percentage name. Is there a way to do that like on just the node?
Ah, I see. Yeah, we can do that as well if you'd like. So you're asking about this?
Yeah, but I guess in that case,
Right. Let us try that. I haven't tried it. I think
we'll get node
but
tree.
I think yes, that's right. Tree and left.
You can't do
That's
it just on the node type.
I'm not sure. Aha. So I guess what you mean is perhaps something like this. Guess what you mean is something like this.
Yeah.
I don't know. Ouch. Right, I don't know okay, this is not syntax. Okay. Let me see. Main no, that's not the one. No. No, but that's a very interesting question. I don't know. I don't know whether that's something we can do. Okay. So James, what would we do now?
I mean, you could look at the auto-generated definitions, but I don't think they're going to say anything useful because we need a guard statement. So
that's true. That's true.
Guard on if X is less than or equal to Y.
Right. Now, one moment. That is true. So you can guard on that. Now, here is something that you perhaps didn't know, is that in addition to checking for less than, there is something called compare, which is what you see here, right? Which gives you three, one of the three results. It's either greater than, less than, or equal. So that's the thing that you see here down, right? So by showing that, I have already shown you the well, most of the work, right? But I would like you to guide me on the generation of that, please. So tell me.
The generation is in using the okay, we'll change the question mark insert. That bit, yes, into case. Because I don't think I guess make case. I don't know.
Yes, that's right. Okay.
And then now the underscore can go to the X.
Actually, that would be compare of X and Y. Yes, that's right. Okay. Now then
then I case split on case val.
Okay. Cool. Now, as you can see, there are three possibilities. Now, if X is less than Y, then Y needs to go to the right-hand side. Okay. How do we do that?
So, just working out my left and my right. Okay. Then,
take your time.
So, did you say if X is less than Y, then which goes on the right? Y.
Y goes to the right of X.
Right. So you want that to be node.
Oh, my apologies. It goes to the left of X.
Okay. Node, and then do you want to? I don't know if it'll generate it. Let's have a look.
Let's see. Let's have a look.
No.
No,
Oh.
it doesn't have.
No. In which case, you want to type the node constructor.
Okay. Instruct me.
Node, and then node arg0 becomes insert x left.
Yeah. Then
And then node arg1 becomes y.
is that so?
Actually,
I think you were wrong, because Y is the one. No, you're right. You're right. Y, okay.
and then right for node arg2.
Okay. Right. Okay.
Lovely.
Okay.
And then the question
um,
is, are you keeping duplicates?
No. That's fine. You don't need to continue from this point. Sander, could you please instruct me on the equality case?
No, sorry, I was a bit distracted.
Oh, okay. So did you follow the logic of binary search trees?
Yes, I think so.
So the thing is that I mean, in a binary search tree, in order to have logarithmic kind of lookup possibility, we we maintain this property in our tree that whatever that is less than the root of a tree goes to the left of it, and whatever that is greater than that is goes to the right of it. And so if a tree already has one element, then we don't insert it again.
Right, so it's just unchanged then.
So instruct me.
So it's just unchanged. Is it just node left, Y, right?
That's right. Now there's also a syntax for that. So let me just change this. There's also a syntax which is very similar to the Haskell one, unsurprisingly. So you can name, or you can bind the original node on which you are case splitting, and now we have given it a name. Then Sander, what would we put here?
Just original.
That's right.
Or
Let's
original.
see whether let's see whether it's also an option here. Yes, it is.
Yeah.
Good. Thank you. Now let's save. Now, Mikhail, can you please help me with this one?
The same as lesson or LT, just swap the node, insert the left node with the right node.
Okay, so let me see. So what do I put here?
Left.
Okay. What do I put here?
Y.
What do I put here?
Insert X right. In brackets.
Very good. Okay, well done. We have our case split thing, and that's our insertion, right? Now, I mean, this wasn't really difficult, but you know, I will ask you when we get into the C++ template metaprogramming to try to do the same using C++ templates, and you would see that the syntax being so horrible, you know, the thing is just out of control. You have to take close attention to so many irrelevant factors to the logic, right? And so there, if you have such a clear way of automated thinking, then, or at least semi-automatic thinking, then it helps a lot. There is the place where you would appreciate this extra help that Idris gives you. Now, I need to draw your attention to the fact that the reason why we could perform this case split was again the totality of compare. All right. So if I take a look to the definition of this, compare as a total function. It always returns one of these three, and Idris knows that, and because it knows that, it can case split on it, and you get the confidence in that you're covering all the possible cases. Okay, so now let's try to go to the alternative syntax with trees. Niels, would you be interested in giving me the more generalized syntax for the tree data type?
The one with that looks like
signatures of the constructors. So we're speaking. Oh, sorry. We're speaking about this syntax, and for the but for your reference, I am now going to copy paste that to the very top, so that you can use that as a role model.
Okay. Yeah. So
Tell
it
me.
would be data, tree, I assume elem.
Yes.
And colon type.
Well, actually, no, sorry. You can do that too, but you wouldn't put it here.
Okay.
You can name it. You can name that LM thing.
Oh yeah.
Probably that's a good idea. Yeah. Yeah.
Okay. Then type.
Okay. Sorry. Huh?
Where?
So tree is a type. It's it takes a type parameter.
Oh, type.
So that it becomes a type, right?
Yeah.
Okay. So what would the type of tree be?
Elem or whatever you want to call it. No? Type.
Well, the matter of naming it is one thing, so we can do this.
Yeah.
But that wasn't the question. Is this all that you? So by doing so, you are saying that elem is a type.
Yeah.
But you're not stating the type of tree. The question is, what is the type of tree?
Type to type. No.
Ah, very good. Come on.
Yeah.
So that's the right type, because tree takes a type and only then it becomes a type.
Yeah.
Right. Now,
But it's no, never mind.
okay. Now then what?
Where?
Yeah.
Enter.
And
then indent however you want. Yeah. Empty is just returns tree. So colon.
Okay.
Tree.
Is that all?
And then you have and then the node. So next line, node.
colons 3 of type elem,
Mhm.
and then the next argument would be elem, and then 3 elem, and you return 3. Of the same type. I guess you have to do that on empty too.
Mhm. Okay.
Uh,
there's
on
so I
empty.
have to. Okay.
I think, so yeah, you need
Right.
I forgot the one on the empty as well. The empty needs type elem.
Very good. Okay. Thank you very much. Now that was great. I think you have already covered what's different. So I have this remark for myself of asking you what's the difference. I think we have already covered what was different. Right. Okay. Okay. Here is one thing that makes you know, in the case of shape, because you know, shape is itself a type. If it would have been that we wanted to return a different type as of the type constructors at the type constructors, then what we would have done was to replace this. Whereas here, for the case of tree, you know, we can still return a tree, but that can be a tree of another element type. Right? Now that's how people usually do GADTs. Right? So that's essentially the reason why sometimes, like for example, when you're doing expression trees, like when you're the easiest you know, the most compact example here is the a calculator. So let's say that you're doing a calculator in Idris, and so you have a number of you know, AST nodes. Let's say that you have a plus and a minus, right? And you have a set of numbers. Now, when you return things, sometimes, and maybe that's not quite the case about this very little example, but sometimes you need to return an AST of another type, right? And when you want to do that, then you have to have the freedom of changing this type parameter. That's what you would want to do. Now, I'm not sure how much of that we're going to see in this course. Right. Now, so there is one extra thing that you can do, which is, well, given that we want to work with binary search trees, and we know that the elements of this tree are always going to be, you know, comparable, right? Or ordered. What we can do is to push this requirement of elements being ordered to the tree itself, so that we no longer need to write it down in every function that works with the type tree. So that is how this other guy came to birth. Well, oh, I need to, and we now have repeated constructors. So what I'm going to do is okay. Now, so you see here in the tree itself, for both the constructors, we require that the element type is itself ordered. And by doing so, we no longer require to write that constraint for the insertion function. Right? Now, here is a quick question. Let me just comment these out. Now, as you can see, in both branches, we are requiring here, no, not both branches, both constructors, we are requiring that LM is ordered. Now, why do you think it is that I can do this and get no error message? Why do you think that in the empty case, I can get away with not requiring that LM is ordered? Jan, would you like to?
Not requiring that LM is odd. Well, since there is no ordering required, you can have whichever LM you want inside of empty.
So
is it because there's just one type? Like there's
what was it, sorry?
in the empty one, there's just there's no
There's just one
other
term
items
in empty
compared.
for each LM. Oh,
I'm not sure I heard you. Let me
say that again,
go
Nils.
to Niels. Let me go to Niels. Niels, what were you saying?
And is it since the empty doesn't have any it doesn't take in elem as an argument? Is that why, since it's not comparing, it doesn't need an ordering?
Well, if that's so, then how do we
There.
I think I now understood what you mean. Like, are you speaking about the thing here, for example?
No, I was talking about the on line 36.
36. Oh, right. So
Yes.
you're saying that there is no empty of something? Is that what you're saying? On line
Yeah,
36?
like the empty doesn't take in an element like an elem, like
Right. Well, so does node do that?
yes,
It does. Where is that?
like val is an elem that is an argument.
Oh,
of
I
type
see.
elem.
I see. Right. So
Mm.
right. So you're saying a value of type LM. You're not saying that. Right. Okay. Well, maybe. Now,
I was also thinking, if I'm allowed to amend my answer, there is only one thing, one term of the empty, which is a constructor of BS tree for each LM.
for
So you
every
only-
type, for every possible type LM.
Yeah.
Okay.
There's only one type. There's only one empty. Yeah.
Okay. Thank you. James, please.
I have two theories. One is the simple option, which is your insert code would break unless it had the requirements for ORD, because it's a dependently typed language. Empty could be BS tree int with all we care. So I think that's right. If not, it somehow infers it. But I think it's just going to error the insert code unless you make that requirement, because you're only
very good.
That's it.
That's true. That's true. So the thing is that you know, let's go to let me comment this one out. Unfortunately, the shortcuts don't work, so I can't use the shortcut keys. Right. Let's let's say that we're still in this world where there is no ordering requirement on the element types of tree, right? Now, and let's now observe the type of empty here. The type of empty is tree of LM. LM still in the typing of that constructor. The LM type parameter is not erased, right? So it's not tree of everything, right? It's tree of that particular LM that we are dealing with in this data type, right? So even though empty as a label for the type constructor can be used for every instantiation of the type LM for the data type tree, Idris still does perform type deduction, and that's the reason why we are allowed to just write empty without any explicit mention of the type, right? Because it performs type deduction. Now, with that in mind, now I would like to remind you that the difference between these two notations was that the second one is the GADT, and I told you specifically that you are allowed to return different types here for the two type constructors. And that's exactly the reason why at the level of the data type, at the level of data type, shortcut still work. There is absolutely nothing wrong with having no orderedness requirement on the element type here in empty, because they are returning different types, and who cares whether one of them is ordered and the other one is not, right? Now, where this becomes a problem is exactly where James said. So if I now uncomment this bit, then I get this problem, In this case, there is no requirement for LM. There is no proof that LM is ordered, right? That's what is missing. Now I leave it to you guys to figure out how you would, if you want to, enforce the orderedness of LM in this case, and not at the very top where you put the right. Jan wants to.
I was going to say put it at the top, but that was
right. That's the quick fix. That's actually the most reasonable one. But provided that you don't want to put it at the top, then where would you put it? Right? You figure that out yourself. Now, yes, the quick fix is also.
Oh no, I thought all the way at the top that we make the BS tree depend on ordered.
Right, I see. So you're speaking about here.
No, at the. Oh, sorry, my screen went black. Let me give you the line number 34.
34. Right. Okay.
That you change out the first type with a value that's an ordered.
Have your play around with that.
Okay, it doesn't like that. Okay. Fine.
Yeah. Okay. Okay. Now we have had some fun with generic types. Now the real fun that is where the dependent typing starts. So, but before getting into that, I'm going to ask Mikhail to give us a joke.
Did you hear what happened to the French cheese factory?
I did not know.
Yeah, It exploded. Everything was left in debris.
Okay. Okay. Fine. Fine. Yeah. So that's what they call a dad's joke. Right.
Very
I what was it, sorry?
It was very cheesy joke.
Sorry. Ah, very cheesy. Ah,
Yeah.
yes, that's
Yeah.
also true. Yeah,
Yeah.
that's also
Yeah.
true.
Okay.
Yeah. Okay, Niels, do you want to give us your joke?
Did you hear about the hand crusher that quit his job?
Sorry, perhaps you would like to approach the mic.
Did you hear about the can crusher that quit his job?
Can crusher that quit his job? No, I did not.
No, he kept saying it was so depressing.
Okay. Yeah. That was a good one. Yeah. Yeah, that was a good one. Oh, Mikhail needs to go. Take it.
Yeah, it's just
right. Okay.
getting some water.
Oh, I see. Okay. Okay. Well, I think we have to wait for him because this is
Cool.
yeah. How long do you think it will take for him to come back, Niels?
No, I just like a couple of minutes.
Okay.
Are you
just
guys in
well,
the? Are you in the
Just around the
second?
corner.
Are you on the second
Right.
floor?
Yeah,
Okay.
Oh, there he is.
Okay.
yeah.
There he is. Okay.
Yeah.
Now,
the water's right around the corner.
is it? But I have a question regarding your name. Is it Niels or Niels?
I couldn't hear the difference.
Right. The difference is that so the difference is in the first version it would be as if there are two S's in the end of Neil. The second one, it's as if there would be a Z in the end of Neil.
I mean, it's like you can just, it doesn't really matter.
Oh, is that so? So in Norwegian, you can say both Niels and Niels.
I respond to most things. If you just say anything in my general direction, I would probably be like, huh?
Right. Okay.
Yeah.
Okay, but I so there's no Norwegian lesson for me to take from that, I guess. No. Okay,
not
fine.
good in Norwegian.
What was it, sorry?
I don't know Norwegian.
Oh, I see. You have an accent. I think you at the dinner you were saying, right?
Yeah, yeah.
Okay. Okay, fine. No problem. Now, thank you very much. Now let's get back to work. So the real difference between Haskell and Idris is in its dependent types. And so here's an example. Let us say that we would like to have a data type for vehicles. And vehicles are of two types regarding their source of power. There are those that you need to pedal through, and there are those that run on the basis of petrol. Right? And I know that in Norway you almost have no petrol vehicles any longer, but please excuse us for the moment. Now, so that gives us this data type, vehicle, which given a power source, right, an instance of this data type, the one that is on line 33, which is an enumeration, it only has two values. Given an instance of these gives us a type, right? So you immediately see that this is a dependent type because, you know, it requires a value for it to become a type, right? Now, given an instance, so what are the constructors for that data type? A bicycle is a vehicle of power source pedal. A car is a bicycle. Sorry. A car is a vehicle of power source petrol, but in order to become that, then you need to have a you know, kind of like the size of its fuel tank. You know, you need to know how many liters that is, and also for a bus, right? So let's say that these are the three possible you know, sources of vehicle sorry, the three constructors of vehicles. Now, one thing here is that you see immediately that you know, the type is dependent on this thing. In fact, we call that the index of the type. So you instances of the type vehicle can be indexed based on their whether their source of power is pedal or petrol, right? There is a classification going on, right? And that's that. Now, provided that you want to, for example, work out the number of wheels of vehicles with whatever source of power there is, then this is how you would do it. I mean, this is more or less something you would expect. Now, here is a bit of unexpected thing. You can have a function that would originally look like a partial function. So you can, given that you can't refuel a bicycle, if you are doing a refuel function, what you get is a vehicle of petrol, and what you return is a new vehicle of petrol. And I have a habit of counting the number of yawns. I think I have thus far counted 2. So the previous one was from Jan, and now it was from Mikhail. So I sometimes even. What was it? Sorry?
I woke up very recently.
Right. Yeah, no need, absolutely not for any excuses. I just you know, it's a measure of how boring I am. It has nothing to do with you.
Oh,
yeah,
just a very tired boy.
Yeah, okay. Well, I hope you can get sleep soon. Now, so as you can see, there is that impossibility for refueling a bicycle. And you can make that explicit. Now, if you leave this as it is, so let me make sure that we have everything. What's the name of this? Now, if I what was the right? I don't recall the syntax for checking whether something is total, but
Big T, maybe?
What was it? No, that gives us the type, but
Is
sorry,
it colon total?
colon total, that should be it. Right? It tells you that refuel is total, even though it doesn't cover all the vehicles, but that's fine because it has only promised to cover the you know, vehicles of petrol, right? Now, so that being the case, the compiler has made its way through the indexation and has been able to figure out the totality. But for the human being, there is the possibility of adding this, which says refueling a bicycle is impossible. So impossible is a keyword, right? Just so the human being, the human reader, can be reminded about this, right? In case they have forgotten, or they have overlooked the typing information at the very top here. right? Now, one more interesting thing about this is that if I mistakenly write this one, then Idris will tell me that that isn't quite the case, right? This is it is possible to refuel a bus, right? Because a bus is an instance of a vehicle of petrol, and we have said that the type of refuel is vehicle of petrol to vehicle of petrol. So that's a wrong usage of the impossible directive, right? Now, so okay, we're good with that. Now let's go see a more interesting dependent type. Now you are all familiar with the vector of Idris, right? The data type vector. It's probably not very difficult for you to realize that vector is something that takes a nat and then a type, and then it becomes, only then it becomes a type itself. So if you, for example, say, okay, what's the type of vect? Okay, well, sure. So import data.vect, right? And then so you say what's the type of vect. You see that it says that it takes a nat and a type, and only then it becomes a type. Now, if I, for example, ask it what's the type of vector 5, it says, because if this is curried, it says that it still requires a type so that it eventually becomes a type, right? And that's the reason why you get this. And remember, we are now doing our own vect, right? Now, that's important because in the C++ TMP template meta programming, we are going to do our own type level vector in C++. So it's important that you understand this bit pretty well. Now, so vector takes two, well, it has two constructors. There is nil, not nils, right? That is a vector of size 0, and cons, or colon is a constructor that takes an element of this type T, right? And a vector of size n of T's, and it returns a vector of one extra element than n, which is the size of this axis, of type T, right? Now, I'm also giving it some names. So let us go through the TDD practice. But before doing that, Sander, would you mind sparing your joke for us, please?
Oh, of course I can. Let's see if we find a good one today.
Okay.
Oh, here's a good one about Bergen.
Okay.
A group of tourists were mildly impressed about the city between the 7 mountains, Bergen, but was surprised about the amount of rain. After talking amongst themselves, they decided to ask a young child who walked past. "Hey, you, does it always rain in Bergen?" they asked. "I don't know," said the boy. I'm only 10.
Right, good. Okay.
Yeah.
That was actually a very philosophical joke.
Yeah.
It was Yeah, I can. I mean, if I get that response from a child, I would say, "Wow, that boy is something."
Yeah.
Yeah, good.
I
Good
thought
one.
I thought the joke that was that it's been raining for 10 years and he hasn't.
Yeah, he still hasn't. I think that was the intention. Was as far as he's only been alive for 10 years, so he doesn't know if it always rains.
Yeah,
'Cause,
but that's
Mm.
that's a boy
Because he
that
hasn't
gives that
seen
response.
the sun or something.
Yeah, well, that then they have. So there's you know the difference between frequentists and so this is about statistics. The difference between frequentists and Bayesians. Oh, that those are two different schools of statistics. Do you know the difference between them? Anyone? James?
It's about what they think they're doing when they do probability. So the Bayesians think that they're sort of slowly uncovering some real function that describes a relationship between things, whereas the frequentists think that all they're doing is working out, well, the probability that if you repeat it, it'll happen, certain outcomes will happen. They don't think they're uncovering any kind of sort of dependency between the real world and their experiment.
Well, you have a point there, but here's my take on that. Thank you. So you see a frequentist when they are asked about a question about how much the probability of something is, what they do is that they count the frequency of that thing happening in the past, and then they give a response based on the division between the number of occurrences and the number of experiments, right? That's what a frequentist does. A Bayesian tries to work out the possibility, the probability of that happening in the future, right? Regardless of the number of times that you have in the past experimented. Right. So there is a joke in there that the once upon a time they ask a frequentist and a Bayesian to work out the probability of dying if one falls down from the top of a 10-level building. Right now, the frequentist says that okay, we'll go to the top and we'll jump down and we'll just count the frequencies. So they jump down, first level, they're not dead, second level, they're not dead, third level, they're not dead, fourth level, they're not dead. They just they come to the conclusion we're not going to die because the frequency is 0. And the Bayesian looks at the height and says, okay, that's that much height, and that's going to cause this speed, and that's going to cause this much force. So when I land on the ground, there will be this much force on my body, and that's beyond my capability. So that means that I will die. So that's them working out the probability to be 1. Now I don't know how we right. So the interesting thing about the boy, the 10-year-old that responded, was that they were Bayesian, right? They didn't care about the frequency of what happened in the past. that was very deep, very philosophical about it. Yeah, thank you. Now let's get back to work. Let's see. Niels, would you mind walking us through the append function? So the idea here is that we take 2 vectors and we append them together to have a bigger vector. So a vector of size n of t's and a vector of size m of t's will give us a vector of n plus m t's, right? Now please walk me through the TDD
Well, we have to start by I can't remember the word, but
Okay.
yeah, add clause is the first one.
Uh-huh. Okay, then
Uh,
you say, okay.
can't you? I don't remember where you like create the base.
Okay.
Uh,
Now, so your hint is the constructors of this type, the data type.
yeah,
Okay. Now, the constructors of that data type tell you that you need to do a case split somewhere. Now, where do you think that somewhere is?
yeah. You can just do it on the x's and
Okay,
ys.
sorry.
Yeah.
And y's. Okay. So I'm going to do a case split on x's. Okay. And you're saying that we also need to case split on y's. Okay. It probably is a good idea to think, did we need the second case splitting? Because appending an empty vector to everything will anyway be that thing.
Yeah, but oh yeah, that's true.
Yeah. So, okay. So we have this then.
Yeah, and then search expression on the first row.
Okay. Okay. What would you think would be the answer here?
The only answer on expression search.
Absolutely. Absolutely. So
Yeah.
you see, Idris can work it out, and the only available option here, you know, when this is an empty, this is a vector of size 0. This is a vector of, well, it doesn't give you the size, but anyway, vector of size m is again a vector of size m, and the only thing that we have there is y's itself, and that's why it can work out, you know, the response for you. Okay, then, but what about then?
We try. I have high hopes for the last solve doing a expression search here as well.
Okay, let's see that. So which one would you go for?
The only one.
Right, that's true. Right, very good. Thank you very much.
Yes.
Now, here's something I would like to impress you with, and I would like to ask you to figure out the reasons on your own. Please. So you're all familiar with the concept of zipping, right? Yeah. So you take performing a zip line. Yes, that's essentially the same thing. So you have a vector of t's and a vector of u. They are both u's, and they're both of the same size. And if you pair each and every element in the two vectors, you get the new vector, right? It's going to be of the same size. So n is the same between the three. What is different is that every element here and here are now paired to be an element here.
Could we? Is it possible to like specify that they can be of different sizes, but the result has to be the lesser size of the two?
I'll leave that as an exercise.
Okay.
Okay. but the thing is that if you want to do that, then you probably don't care about the sizes, and then your data structure of choice is list rather than vectors.
Yeah, okay.
Right?
I mean, I guess you could have A, B, and C instead of N of the size, right?
if you want to.
Right. Yes, you can make this N and M, and then this would be minimum of N and M. Right.
I thought you could just have 3 sizes, like.
Well, then you're not being very precise. I mean, in vectors, you want to be precise with sizing. So, yeah. This is rather. Is this the syntax? I'm not sure. This is the syntax. Yes. Okay. Yeah. Now, anyway, I'll leave that for an exercise. What I would like to impress you with is that you can just ask Steve to work out the complete definition. Right? And it's on you to work out the reasons. And hint, there is a book you can read.
Yeah, I got it yesterday.
Yes. Okay, very good. Now let me see. I think there was some extra things here at the end of the chapter that I wanted to tell you about. I'm not going to make it. It's the timing is not right because I need to leave soon. But the thing is that you can also put guards on. Right. Let me just maybe show that to you, but I'm not going to tell you how. So let's say that we're here, and let's say that we import data vect. Okay, then if I ask for the third index, sorry, for the third element in this list, right, I get 4, but if I look up the 10th of them, then it says that, well, sorry, dude, but 10 is out of bound, right? Because at the compile time, it can figure out that 10 is out of bound, right? And so, but this is only at the compile time, right? Now, there is some extra excursion here that you can go through so that you can you can kind of enforce this yourself on the vector that we are implementing. And given the time pressure, I would like to ask you to read that yourself. And afterwards, in the book, there is a subsection, the subsection 4.3, that I would anyway want to ask you to read on your own. It's good practice for learning TDD. It's good fun, and kind of it's about seeing it in action with a more real world example. That you read on your own. There is no much of extra syntax or theory that I would need to show to you. So I'll leave it as I do it yourself. Any questions, please? No? Okay. Then I can stop the sharing and also the recording. Right. If I may.